So I have Lisa source code here that we're going to be releasing. I guess for the first thing is, uh, what were your thoughts looking at it for the first time in 30 years?
Well, I unpacked the zip file and looked at it this morning, and I thought, whoa, there are like hundreds and hundreds of little bitty files. And they all had cryptic names on them that didn't mean anything to me. And I figured I found one that had QD in the name, so I figured that must have something to do with quick draw. But then I looked at all the hundreds and hundreds of files inside that folder, and it didn't look like the code that I worked on. I'm sure it is, but when I worked on QuickDraw, it was not all fragmented up into little bitty pieces like that. I worked on the window manager, event manager, and menu manager in Pascal, and then QuickDraw was almost all assembly language for performance reasons.
So maybe we could take a look at something that hopefully was one of the things that you worked on, and you could tell us what you think is particularly interesting and why.
Okay, maybe regions.
Regions. Okay, so can you see my screen here?
Yes, I can, and your names have nothing to do with my names.
Well, hopefully this is something familiar. So let me open this.
Okay.
Just a little bigger here. Okay.
So what is the concept of regions? When you have overlapping windows, you may have to draw into a window that's not the frontmost. And so it's not a rectangle of drawing space, it's an arbitrary shape, could have 7 other windows on top of it, and one little sort of puzzle piece part of it is showing. So in order to draw into that non-rectangular area, you basically what you need is a write protect bit for every pixel on the screen. Now the Lisa display had 1 bit 720 by 360 pixel display, and we didn't have enough memory to have a write protect pixel for every window on the screen. But what I figured with regions that made it really work was that most of the writing is done top down. If you do it in because 32 adjacent pixels are in the same long word, you can write most efficiently by writing in slabs. If you're drawing a fat line, you draw a slab and another slab and another slab. But you can do that top down. Then if you notice the shape of the uncovered areas, they're sort of like, not too far from rectangles. They have, an L shape sometimes or a more complicated one. But basically, one scan line, its sort of write protect, the scan line for that write protect is the same as the one above. It's the one above. And then here's a change. So what regions did was provide a very compact way to store the changes in the shape of that writable area. And that allowed us to pretty much draw almost the same performance as if we were clipped to a rectangle, but to do so to an arbitrary region. Then we needed the math for adding and subtracting these. You start with a window and you subtract the ones that are above it to create this one. And this is where the QuickDraw graphics primitives and the window manager had to be in collusion with each other. Because the window manager, when you drag a window and let go of it, it has to recompute the visible regions and structure regions of each of the windows underneath it and communicate that in a way that the graphics primitives can respect those. And regions was about that. And it was many years later, I was sitting in a hot tub up at Harbin Hot Springs with somebody from the Xerox team, and they said, "How did you draw into non-rectangular areas?" And I said, "I didn't know you couldn't do it. when we went to see the visited Xerox, we saw that happening. But really, what they were doing was drawing into the behind window and then redrawing each and every one of the windows in front of it. And sometimes, when you don't know that something can't be done, it empowers you to come up with a way to do it. I was proud of Regents.
Thank you. That's a great story. Is there something else we want to take a look at?
Lisa had non-square pixels. We were very tight on memory, and so given that we had 320 scan lines, we made 720 wide, and the pixels were sort of half again as tall as they were wide. And so whenever you wanted to draw, like one of the applications in the Lisa suite was a bar chart and pie chart maker. And so they had to be able to draw an arc of a circle, or filled in arc of a circle. But because of the non-square pixels, it really was an arc of an ellipse. And so I figured out a way that we could efficiently generate the slabs of that. And basically, the x-coordinate is sort of the square root of radius squared minus y squared. And we didn't have floating point processor, and floating point would be thousands of instructions to do just one floating point add. So what I found was a way in fixed point math, I could simply do one add and generate the next one, using the fact that x squared is the sum of the first x odd integers. So if you kept a little table of x and x squared, you could generate the next one by adding 2 onto an odd number. Add 2 onto odd number, add this onto there, and in a few adds, you could get the next thing. So we ended up, I made it so that you could draw arcs of an ellipse, and it would look circular on the Lisa's non-square pixels. Then later, we wanted to do rounded corner rectangles. I didn't think they were sufficient graphics primitive. They would occur all over the place. So Steve Jobs took me for a walk and said, look, here's a rounded corner here and a rounded corner there. We get to do a no parking sign, and all you see, oh, okay, they're all over the place. And the next day, I came in, the same thing that drew arcs of an ellipse could now draw arcs of a rounded corner rectangle, because all I had to do was, if I was going to draw this, just start the left and right sides farther apart, and when I got to halfway, take a break in the bumping and continue later. So that code accomplished a lot of stuff in a small space.
One thing I'm curious about is, why did the Lisa have rectangular pixels, not square?
Oh, okay, so we wanted to draw text well. So Lisa was the first time that Apple was doing proportional text, where an I is narrower than a W. And on the computers before, it was a ROM character generator. In fact, the Apple II only had uppercase. This was an uppercase keyboard only. And every character was the same width. But when you have a variable width, then you want to be able to, you can squeeze in more text and you can make it fit more smoothly. But we saw that the x-axis was, for a limited number of pixels, the x-axis gave you more text ability. And so we went with a more compact. If we had lots of memory, we would have just made them square pixels and just used more on the Y, so that we had the same in X and Y. Later, the Lisa XL, because it wanted to be Macintosh compatible, had to go to square pixels. They had to redo the hardware, make it a different number of scan lines. In fact, the first scan lines on the Lisa had a hardware mechanism for smooth scroll. They had 320 pointers to where the data is for each scan line. And so to smooth scroll, you just updated the 320 scan line pointers, as we were really concerned that we wouldn't have enough performance to do smooth scrolling in a word processor. But when we went to overlapping windows, all of that had to be thrown out. The hardware was there in the first Lisa, but was never used because you can't scroll the whole line. You have to scroll just within that one window. So we never used that.
Oh, thank you. I'm going to open up some of the quick draw files and
Okay.
see if you can tell us what's going on here. Let me move this over here. So I don't know does any of this look familiar?
Yeah. So what you're looking at here are constants that define the transfer mode when you copy a block of pixels from a source to a destination. Now that could be copying from a font onto screen, or from a screen onto screen for scrolling, or from a screen to off-screen buffer to save what's there. For example, when we pulled down the pull-down menus, we saved off the pixels underneath them so that when you let go of the menu, it could put the pixels right back. So copy bits had different transfer modes. And what we're looking at there is the transfer modes of moving the pixels, or ORing the pixels, or ANDing them, or bit clearing them, different ways of doing a bit transfer where you're copying a block of pixels. So a lot of these are the public interface for QuickDraw that Pascal programs could call. And they would call this interface, but the implementation was all in assembly language. And this is an interface file that would be linked with or compiled against when developer was using the Lisa toolkit to develop applications.
Okay. Is copy bits, is that similar to the BitBlit?
Same general idea.
Okay.
And also the same as copy bits in Apple II Pascal, the UCSD Pascal system that I ported to the Apple II had copy bits in it, and it was pretty much the same as BitBlit.
Okay, cool. All right, let me switch to this file here. Make this a little bigger. Okay, so this looks like the implementation part of it. We were just looking at the
Make it a
interface.
little smaller. It's
a little smaller.
It's wrapping funny there.
Okay, there you go. Okay, so these are. This looks like the.
This is the FM. Anything starts with FM is font manager.
Oh, okay.
So when you make a request on the font manager, you're saying, here's the name of the font and the size and the extra properties like bold or italic that I want. And this is going to return an output record that tells you here are the pixels and the leading and properties of the characters in the font.
Okay.
So QuickDraw had to work closely with the font manager. Fonts were basically a block of pixels and some descriptors saying, okay, the A character starts here, and the B character starts here, and the C character starts here. So when you go to draw a B, you start at the beginning of B and stop before the C and copy that to the destination. And QuickDraw had the ability to now add extra ornamentation on that, like copy it but with a slant for a fake italic. If you didn't really have an italic font, you could leverage the limited number of fonts you had by doing italic on the fly or bold on the fly. It would draw it and draw it again in bold, in OR mode, or even it had outline and shadow and things like that that you might only use for things like labels on a pie chart or something.
Yeah, thank you. Those built-in styles are some of the things I remember about using the classic Macintosh. That
Trying to get as much mileage out of a font as you can.
yeah,
We didn't have PostScript.
right,
We couldn't have afforded it either.
right. So I'm looking here at looks like these are called graph port routines.
Okay, a graph port was the context for drawing. When you want to draw into a bitmap, this could be the bitmap on the screen, but it also could be an off-screen bitmap. You might want to image something and then copy the whole results onto the screen or something like that. You would instantiate a graph port. It's a graphics port, and it had all of the context of that. For example, if you draw a character, it would then bump the cursor. So if you draw a character again, it would bump it. No, so that's one of the things that it would have. A graph port also had clipping regions. What is safe to draw into? It had the visible region and structure region that were generated by the window manager for it, but the application-specific clipping region. It had things like the current pen mode, the current pen location. So lots of just the sort of all of the state variables about a drawing context. I think more modern programming would have called it a context.
Right. Yeah, I think that's what PostScript refers to it as too. Similar idea. Let's see, and just scrolling down, any other things that stand out to you that you want to highlight? You know, like line drawing routines, rectangle.
Oh, I always like to get Penn State.
Get Penn State.
It sounded like a football cheer.
Where is that?
But I mean, get me the
oh, right.
current state
Penn
of the,
State. There we go.
the drawing pen.
Yeah, get the state of the pen. Get Penn State.
So one of the things that these graph ports let you do is record without imaging. We had a very slow processor on the Lisa and slow process management. If you had something that was drawn into a behind window, usually that application was asleep. And what happens if somebody moves a window over and you have to reveal more of that and some more stuff has to get generated? Well, we didn't have enough memory to have that stuff, already sitting there off screen, and we just copy it. So what we did is made something called pictures, which were a recording of graphics operations. And you could say, open picture means start recording. It's sort of a journaling. Do all kinds of drawing things, but no pixels get generated. It's just making a compact little list of operations, and then close picture. Now you've got a picture handle here, a piece of memory that has a recording of those operations. And now, without waking up the application that's asleep, the window manager itself could say, oh, this guy's got a picture for it. I can redraw the newly uncovered part just by playing this picture.
Wow. That's really fascinating. So I'm looking here and I see copy bits here, and I see a bunch of stuff on regions. So all stuff that you referred to earlier.
So they were sort of verbs and nouns. So frame meant outlaws, like frame a rectangle is just draw the edge of it. And whereas fill meant fill it in solid. And erase meant clear it out. And invert regions is it was only one pixel, black or white. So it meant if it was white, make it black, and vice versa. And paint region means put the current pen color. And we call it a pen color, but it was either black or white. Or actually, we had fill patterns. Because we didn't have grayscale and we didn't have colors, we sort of faked it with 8x8 repeating texture patterns. So when you'd say paint that region, it would be painting it with the current pen pattern. So you could break down a lot of the operations into is it one of the verbs is frame, paint, erase, invert, or fill, and then the noun part, this could be a region, a rectangle, an oval. So you'd have frame, a poly is a polygon. Arc is an arc of a circle. So rectangle, oval, so you can kind of pick and choose the verb and the noun, and that made it a little more consistent interface for dealing with the graphics primitives.
Yeah, thank you. Let me see if I can find the actual assembly files for this. Where would that be? Let's see.
You know, the thing that I'm most proud about QuickDraw and the Lisa Window Manager, Event Manager, and Menu Manager is when they had to be ported to the Macintosh, they were handed over to Andy Hertzfeld, who translated the Pascal portions into assembly language, and that all of that occupied about 2/3 of the original Macintosh ROM. But the thing I'm proud about is I had 0 questions from Andy. Every line of code had a comment on it that explained what it was doing, and I don't write tricky code. I write clear code that somebody else could walk through and understand and read. And the proof of that is that Andy was able to migrate the code and not come back to me with questions.
Thank you. So I think all of the individual things are broken up into all these files. So I think I found the round rect file.
Okay.
So I see. So I see the it has the.
So roundrec will collect the parameters, like how rounded the corners should be and which rectangle it should go into, and but then it will call a common routine that did the real work. The real work could do an arc of a roundrec, and the Pascal interface would sort of gather the parameters and then call the common routine.
Right. Okay.
When the Lisa was being developed, we were trying to figure out when was it going to be done. We were really in a rush to finish this, get it out the damn door. And so we started doing code measurements. How many new lines of code did you write? And that measurement theoretically should get smaller and smaller as we get toward completion. And 1 week, so each week, every member of the team had to submit a report on how many new lines of code they wrote. But I found a way to coalesce and refactor and take a bunch of stuff that was separate and make it call one common routine that could do the work. And so that week I got to report negative 2,000 lines of code. So Larry Tesler said, "Okay, Bill, you're exempt from this reporting your lines of code."
That's something that modern software engineers would pride themselves in maybe in doing.
Yeah.
Yeah.
And still make it clear.
Right.
No tricky stuff. Don't make it so that somebody else in following in your footsteps can't follow what you did.
Right. Yeah. It's extremely important. Maybe can you discuss the process that you went through to write the code for QuickDraw and the other things that you did?
Well, yeah, a lot of it was get it working, even though slow, and then figure out where it's too slow and make it faster. And so I used a technique called PC histogramming, where you have a timer-based interrupt that sort of taps the processor on the shoulder and just notices where the program counter is and puts it in a bin and just stores all of those. And you run a sequence of operations you're trying to do. You're trying to draw some text in the word processor, or you're trying to scroll something, or you're trying to draw a pie chart or something. And doing those operations, you're gathering program counter histogram. Now you run another program that knows the symbol table of the code and knows the program counter listing and puts it in bins and says, this is where we're spending all the time. And you say, the places that you weren't spending a lot of time in, don't bother optimizing those. So my motto was measure before you optimize. Know where you're spending the time. And then if you're spending a lot of time in this section of code, go unroll the loops and make things like, instead of do this, decrement a counter, see if you're done, maybe branch around. Instead, you could make, if you know that there's only 13 longs across the whole screen, the maximum count could only be 13. We'll make 13 copies of the code. And at the head, say how many we are and jump into it part way and do that many without a loop checking and counting kind of thing. We call that an unrolled loop. And again, measure, because once in a while, because of the 68,000 cache optimization, that unrolled loop was slower than a decrement and branch operation. So you had to kind of always measure. But my notion was get it working first and get it to be reliable, and then figure out what does it take to get it to be performant, and kind of separate those two tests. Think about it while you're doing the algorithm. The other thing is that you get factors of 5 faster by coding something, unrolled loops and things like that. You get factors of 20 if you stop doing something stupid. If you just think of a completely different way of doing a job. Don't do something that requires a floating point operation, that kind of thing. So try to think outside the box and think what is it really trying to do, and aim at that, and you can, because a lot of what I was doing was about performance. If it hadn't been high performance, then the graphical user interface just wouldn't have worked.
Right. Yeah.
We didn't have accelerators.
Yeah. So let's maybe talk about some of the other things that you worked on. So you said you worked on the window manager and event manager, and what else was
a
it?
menu manager.
Oh, menu manager. Okay. Let's see, maybe I could try. See if I can find.
Let's look at the menu manager.
Where would I find that?
Well, I don't know. You've renamed all these files with 4-letter words that don't make any sense.
Okay.
I'm sorry.
maybe instead of us finding it, or while I'm trying to find it, just talk about.
I'll tell you
it
some examples of this. Okay. We're trying to support applications. Now, it's very important that we had 7 real live applications we were writing, because they had to pull the system tools had to support real applications. You can't make system tools without something that needs the tools, right? It has to be a pull. So you get to a point, for example, say the word processor. It needed a fair number of functionality. You needed to have editing operations, and you needed to have filing operations. And so as we went through different ways of structuring the menus, our very first menus were actually copied from HP terminals that had 12 soft keys. Well, they had physical keys on the keyboard, and we would draw little labels for them on the bottom of the screen. And what we found is you press one and that relabels the others, and press another, that relabels. It was very, very error prone. We tried to do that, and people just screwed up over and over. It was terrible. We finally got rid of the soft keys and went to a menu kind of system. And initially, the menus were across the bottom of the window, and then they moved to the top of the window. The problem was that if the window was narrow, you didn't have room for all the titles of the menus. And if it was near the bottom, then the menu couldn't have all the items showing. And so at one point, I brought in a prototype to show Larry and the rest of the group where the menus were all moved to the top of the screen. And now you had the full width and the full height. So that's an example we found, and that one stuck. That one gave us then the breadth and depth. Oh, here's a fun one. I went to visit Doug Engelbart. So back in my undergraduate days, I had used an Engelbart mouse down at UC San Diego. So was familiar with mice, and Doug Engelbart invented the mouse. And I went to visit him, and he had this augment system that was very high powered, but really hard to learn. And it was really designed for knowledge workers, and it wasn't user friendly. It took a significant investment to learn how to use it, but it was worth it because it gave you power. And he coached me. He said, the problem is you want to make something that is user friendly, that's easy to learn, but you don't want it to ultimately block your ability to perform. You want to be high performance as you get to be more expert. And he said, think how fun, it's not easy to learn to ride a bicycle, right? You're gonna, get some scrapes and cuts learning to ride a bicycle. But when you finally master balancing that thing, it's worth it. You can go faster and farther on your bicycle than you could just by walking. And so he said, think about that as you're doing this design. Don't just make it user-friendly. Also, provide some way to allow growth path for an expert user who's using it over and over and over. And that night, I added command keys to the pull-down menus. They didn't have them before, but now there was a little Apple symbol and a letter that corresponded to the keyboard, and every time you use the pull-down menu, it's sort of giving you a little coaching. By the way, you could have gotten to this by that letter. So the menu system evolved and developed as we.
So did you come up with
progressed.
like the actual assignment of like ZXCV for undo, cut, copy, paste?
I think Larry Tesler might have suggested that because they had to be. If you're right-handed and your hand is on a mouse, your left hand is a better one to do command keys with. So what's near your left, if you want to press the command key with your thumb, what's near there? Mm-hmm. And C for copy made sense, and X kind of made X sense for cut it out. V is sort of an opposite of an editor's insert mark, and P for paste. And Larry Tesler, I think, I'm not sure I remember, but I think he's the one that suggested those particular ones. At one point, we wanted to have keys on the keyboard that were cut, paste, copy, undo. And I think they just felt too specialized, and we ended up using command keys instead.
Okay.
At first, we had the Apple key, Apple on this letter. And when they did the Mac, Jobs said that was misusing the Apple logo. And so he made us use a different symbol on there. And the little freeway interchange sign, that comes from, Susan Kerr came up with that, and it comes from Swedish maps, where that's a symbol for a feature, like a special place you might want to visit because it's a tourist interest point. So that was the feature key instead of the command key.
Yeah. Okay. So I did find the menu code and also the window manager codes. Mm-hmm. So I don't know if we could just take a quick look at this and see describe what you're seeing here.
So one of the things in window management is, how do you know where characters go if you type on the keyboard, right? You need to have a place that the character is going to go and an active window. And we needed some way to highlight. It's not obvious if you got two side by side, it's not always obvious which one's on top. When you type, where's it going to go? And the one question is, which window is it going to go in? So we started highlighting the tab, and at first it was just a little highlight, then we did a much more bold highlighting. And then what we found, when people would point, so with a dumb terminal, the old text editors, all of the cursors were a block cursor that either like blinked a character or made a block of white or something like a block of invert. And what we wanted when we pointed, we wanted to click to insert. You want to click between two characters. So initially we had an arrow cursor, and we found that users would always point at a character, and then they weren't sure, was new typing going to go after that character or before that character? And so we switched to an I-beam cursor, and that I-beam cursor encouraged them to point between characters and then get an insertion line that they know that's where the characters were going to go when they typed. So that was, a step we made. Stepwise, incremental refinements. It took us a while to figure that out. Window managing issues. A lot of the window manager's job was keeping track of what areas are exposed and making that available to the the quick draw graphics routines, so they knew not to overstep their boundaries and not write in one of the upper windows when they were drawing they were drawing a picture, but they were going to draw it with a new clipping region, a new visible structure region, so that they could not trash the frontmost window.
Thank you very much. That was really, really fascinating.
You're welcome.